చెప్పనా స్టార్ట్ అయింది అయింది ఆల్రెడీ అయింది. హలో వినపడుతుంది సార్ మీకు? హలో హలో సార్ వినపడుతుందా మీకు? హలో హలో వినపడుతుందండి? కెన్ యూ హియర్ మీ? హలో 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 హలో కెన్ యూ హియర్ మీ? హలో 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 కెన్ యూ హియర్ మీ సార్? హలో ఓకే. Just see here. Okay. Today I will start here the concept of now. Here the content is mathematics by methods of applied mathematics. Okay, here. See here again. What is the mathematics of applied mathematics? This is the purely MSc mathematics. This is the paper of 8th B. Paper is methods of applied mathematics. Now, first of all, we have to begin with what is the now methods of applied mathematics is defined from the basic concepts of calculus. Anyhow, this is the first class and welcome to all. So good morning to everybody here. Now, here the methods of applied mathematics is defined from calculus part, that is the differentiation and the integration. This is the mathematical oriented and the physical oriented concept. Now, here what is the concept of methods of applied mathematics? There are so many applications by using the mathematical combination and physical combination, and how to explain the methods now according to the mathematical applications in physics, physical phenomena. Now here the calculus reason is the differentiation and integration. Now here the first of all we have learned in the basic concept is in the differential equations. First formation of a dA, how to the formation of a dA. There are so many differential equations to form from the concepts of just like the geometrical expressions. Now here the example is formation of a dA and all parabolas, smooth etc. origin Posse on y-axis and Posse on the x-axis, and some other ellipsis concept is also here. Okay, sir, can you hear me, sir? Okay. Now here the formation first order and the first degree is also here. Now first order and what order of the first degree is also here. Now at the same time first order and the higher degree concept. Now these concepts in the differential equations. Now here the differential equations can be defined now it varies formation of a dA and now here the ordinary differential equation and the partial differential equation. Now in higher order degree is there. Okay. Now what is the main concept? What is the main aim of methods of applied mathematics? First of all, we must know here. Now and at the same time, what is the introduction and the concept of methods of applied mathematics? And now some other linear equations must be utilized in variable coefficients and constant coefficients is also there. And the simultaneous concept, the simultaneous equations, how to solve the simultaneous equations. These differential equations must be explained here. Now, suppose in the numerical analysis concept is there. Now, with according to the ordinary differential equation and how to find the real root of an equation. Now, these are all some application oriented. Some other example is also now here regular falsy method and the Newton-Raphson method and bisection method at the same time that is also called the Bolzano method. And entire these concepts and Adams-Bashforth method, Millet method, and the predictor character method, entire these concepts must be the concept of ordinary differential equation by using the initial conditions. In the same manner, in the physical phenomena, according to the above ordinary differential equation concept, a wide range of applications in the waves and oscillations and the string theory and the mechanical oriented, that is the fluid dimensional theory is there, and the quantum mechanics and classical mechanics, some other engineering applications also there. In the same manner, some special functions will also applied in the concept oriented, that is the part of the special functions. Now here the basic concept is already here. What is the basic concept? Now the ordinary functions are also there. Now here the special function concept is that must be calculated through the differential part and integration oriented. Now especially in the beta and the gamma function, just we have to observe. This is also one of the, there are so many applications here. Now that must be used in such a number of regions, either physical phenomena and some other regions. Now here the beta and gamma functions is completely dependent upon the proper and the improper integration is there. And some other differential part, the second order differential part is, and the higher order differential part is also must be explained. Legendre equation, Bessel equation, and that is the Lagrange polynomial and Hermite polynomial and Kirchhoff expansions and some other expansions also here. Now, according to that, the dimensional concept theory is there, oriented application. Now that is the solid geometry is there. Now enter the geometrical concept must be analyzed in the geometrical oriented, calculated with the concept is there are we are taking the hyperbolas and the ellipses, much more applications here. Now those concepts must be derived, must be the derived part. Now, through the calculus of variations means that is the functions of several variables. Suppose here the calculus in the one of the regions calculus is vector calculus. Now, what is the vector calculus? Calculus means that is the combination of vector differentiation and vector integration is there. Especially in numerical calculus means that is the numerical realization is also some we have know that arguments and entries according to that. Now we have to explain the such a differential concept is there, and according to this one, now difference tables are also constructed, and Newton-Gregory interpolation formula and backward interpolation formula. Now entire these concepts must be defined, and at the same time Lagrange interpolation formula and also Gauss forward, Gauss backward. Entire these concepts are also in numerical calculus. Now here in the dimensional concept is what is the x and what is the y. Now according to this, now we have to elaborate the calculus of variations. Now here that is what is the x. Now suppose you are taking the function is there y equal to f of x in any one of the function, and v of that function, here the x and y both are variables are there. Here x is called in horizontal line in dimensional concept. Every dimension must be represented as one of the line. Now, in the basic and the basement line is called horizontal axis. Now, here all those values are called x values. Now, that is called independent variable. As in the same manner, here y is the dependent variable part. Okay, that's enough. Now, according to these arguments and converting into the differential part is also elaborated to find a real root of an equation. Now, from transcendental equation is also there. And according to this, from ordinary differential equation, first order and first degree is there. Now, already later we have to explain bisection method, Newton-Raphson method, Ricola-Falsi method. Entire these methods must be defined, especially ordinary differential concept. Now, here through the initial value problems, that is the initial conditions are also applied here. Now, more applications must be utilized. And according to the boundary conditions applied in this region, it's the differential part, irrespective of the nature, either mathematical or physical combination also there. Now, without mathematics combination and with mathematics combination is here. Now, enter some physical concepts already we have in undergraduate level is there. See waves and oscillations. Now, there are so many applications must be utilized through the differential part. Okay. Now, in the same manner, fluid dynamics is also there. Fluid mechanics. Entirely, this is partial differential equation explained in some other strategies. Okay. Now, much more applications here. Just you have to see this one. Now, much more applications utilized in methods of applied mathematics. Now, here the application oriented and their methods. Okay. In this last part, integral equations applied in Volterra integral equations and Rednam integral equations also derived. Thoroughly practiced differential and integral concepts, Fourier transformation and the Laplace transformation with initial value problem and the boundary value problems are also there. And according to that, we have to elaborate jet transformation and Hankel transformation also there. Entire these concepts must be involved in this syllabus of methods of applied mathematics. Okay. Already some of the reduction formulas based on we get the result as a directive part. And here the appliances, aerospace engineering is based on linear algebraic levels. Now, at the same time, in algebraic concept, you have the research oriented in algebraic part is especially now 22nd stage of tensor products. Okay, in tensor calculus is also given on the syllabus is also there. Tensor calculus 1 and the tensor calculus 2 is there. Now, much more, this is also entire the applications, methods of applications and applied mathematics is also much more useful in further generation and also this generation also. Now, each and every part must be elaborated here. Okay. Now, this is the concept of methods of applied mathematics, and it is completely based on the calculus part. Now, that is the especially calculus means that is the combination of differential and the integral part is here. Okay, that's enough. Now, here what is the syllabus of methods of applied mathematics? Now that is the first one, calculus of variations. Now calculus of variations means now from the beginning, what is the concept of calculus of variations? Calculus means now through the differential part is here. Now that must be how to variate the how to must variate in calculus region, especially here the Euler concept is also there, and that Euler equation for the in the internal and extremum points also there. Now those points through the function and other forms of Euler equation and the solutions in the special cases. Now that is the from the beginning part of calculus of variation is Euler equation. Okay. Next one, Lagrange multiplier method. This is also one of the important concepts and the geodesics. Geodesics. This is the first part of calculus of variation. And the second one is the calculus of variations too. Now, here the introduction is variational problems with several variables as functions of single independent variable. Now, already here there y equals to f of x be any one of the functions. Those functions must be here x and y. There are two variables, and x is the independent variable and y is the dependent variable. And those, according to that variable, according to that function, how to define the differentiation part already we have to know that in the lower class level and undergraduate section is there, and through the function and how to determine the first derivative, second derivative, third derivative, and so on, nth derivative of the function is also there. And such type of functions must be defined in the Euler equations. This is also numerical concept, Euler method and Euler summation formula. Now that is the effort Euler method and how to find out the n+1 functional value. Okay, through the given the kind of functional conditions and its applications. Next one, Lagrange multiplier method, and the third one is the geodesics. Now, in the second unit is calculus of variations. Now, in this session, first of all, we must know what is the syllabus of methods of applied mathematics, and according to that, how to define the concept of concerned topic is here. Now, this is just a series one. Now, this is the calculus of variations too. Now, there is variational problems with the several variables and as functions of single independent variable. Now, functions involving higher order derivatives. Now, suppose y equals to f of x, the function is there. Now, how to define the f dash of x, f double dash of x, and the nth derivative of the function is there. And according to the nth derivative of function is also practiced in lower class level, in intermediate levels is also there. Okay. And here, functions involving higher order derivatives, and according to that, Hamilton principle, one of the important concepts in calculus of variations in second part, and the Lagrange equations of motion, and the third one is the variational problems for functions involving double integrals. Now, this is third one, multiple integrals. Now, this is one of the important concepts in multiple integrals. Okay. What is the multiple integrals? It is completely based upon the 2D vector calculus is there. Already here vector calculus means vector differentiation and vector integration. And at the same time, calculus part is also from the beginning moving of a particle, how to define the position of a vector, and at the rate of the timing, the rate of changing with respect to the time, and how to find out the differential vector geometry. Okay, that is the first of all, what is the position of a vector function? To find out the dr by dt and the d square by dt square and the dq bar by dt cube. From here, the expression of r dash of r bar t and r dash of t, r double dash of t, r triple dash of t, whatever it is, through the position vector. And according to that, vector differential geometry also explained in further units are also there. That is a tangent curve. Tangent curve is there. And according to the tangent curve, we have to explain the unit tangent and principal normal, binormal. And these fundamental unit vectors must be explained in the apprentice array formula. This is one of the important concepts in further units. Okay, and vector integration is also there. What is the vector integration? So integration of vectors, vector integrals, vector calculus means vector differentiation and vector integration. And according to the vector integrals, that is also well practiced in the UG level. Okay, line integral, surface integral, volume integral. Okay, now those integrals, according to those integrals, we have to explain the Just see in the third unit, these are all multiple integrals based on the single integral. It expresses the one-dimensional part, either x-axis, y-axis, or z-axis, and you have to represent one of the line. When the what is the vector? When the initial point coincides with the terminal point, that is called an integration. And according to that integration, we have to explain that integral of the line is also called directed line segment. What is the directed line segment? So simply that is called a vector is there. Now here the I bar, J bar, K bar, these are all three mutually perpendicular unit vectors. At the same time, position vector. Okay. Now those vectors we have to explain those dimensional segments. That is the line segments. Now suppose x-axis being one of the vector region is there. Now that is the direct that is one of the directed line segment. That is one of the line integral. Okay, that is single integral along the x-axis, along the y-axis, and along the z-axis. And here the double integral part, and the third one is the triple integral part. Okay, that's enough. Now here, what is the change of order here? Now those three integrals, that is line, surface, volume integral, then according to that those integrals you have to explain the single integral, double integral, triple integrals are also there. And according to here, change of order of integration, in replacing y by x and x by y, you are taking the in the order of integration. First you have to take in the there are two types of the part along the y. First you have to take the y, and you have to take the x. Now that is the order of integration, change of order of integration in a double integral region. Okay, that's enough. Now in the same manner, polar coordinates, how to express the polar coordinates, how to change the polar coordinates, and how to solve the type of double integration. At the same time, application of double integrals. And here the centroid of area and the movement of inertia. Now this is the physical phenomena, how to applicable the double integration in the center of area and the movement of inertia, and explain the triple integral concept also there, and there is also volume integrals. Okay, volume of the part. Now this is the Fourier series. Now this concept is also, first of all, you have to, what is the concept of introduction here? Fourier series, change of intervals. Change of intervals means integral A to B. There is the closed interval of the path. How to change of intervals, and what is the even function, what is the odd function. Suppose odd function is f of minus x equals to minus f of x, and f of x equals to f of minus x equals to f of x. That is the even and odd functions are also explained here in the Fourier series. Now half range series, how to explain the half range series, and that is the complex form. Okay. Now here the fifth concept is transform techniques 1. Here the kernel product and the convolution properties. And the second one is the Fourier integral formula and Sturm-Liouville problems. Sturm-Liouville transforms are also there. Now this Liouville is one of the mathematicians. Already he was explained so many concepts are there in the especially bounded and function in the complex analysis region. Okay. Now according to that here, that is the transform techniques is also one of the concepts. Sturm-Liouville transformation is also one of the important parts, and according to that, how to find out the inverse transforms. Now here the next one is there, the last part is there, Fourier transformations. Fourier transforms means that what is the Fourier transform? First of all, we have to define the definition and the properties of Fourier transformation. Next one, convolution theorem. What is the convolution theorem? This theorem is also must applicable in the same Laplace transform is also see here. Okay, that according to here the convolution means that is the resultant of two functions. That is in between those functions in between star as one of the composition is there f star g. So that is also called resultant of f and g. Now how to define the convolution theorem and the partial identity and applications too. So already I have to explain here what is the boundary value problem. Those boundary value problems must be explained. What are the applications to boundary value problem for above theorems? Okay. What is the Fourier sine transformation and the Fourier cosine transformation? Now those definitions are also defined, and also at the same time some problems are also practiced here. Okay. Next one, Laplace transforms. In the same manner, what is the existence of Laplace transform definition? First of all, we have to define the integral transform, and according to the existence of linear transform and some other properties of Laplace transforms. And what is the inverse of Laplace transformations? And the unit step function. How to divide the step function? Now, so that is called unit step function is also the same manner. Here the convolution theorem is there, and the unit impulsive function. Okay, this is the Laplace transform part, and the applications of Laplace transform and the ds direction is there. What is the here the some applications, some special functions and their Laplace transformations. Now initial value problem involving linearity part, and initial value problem with the impulsive forces is there. Now what is the force part is how to involve the force part in through the Laplace transformation. Okay, how to find out the force. Okay, now for some IVP problems with impulsive forces. Now at the same time simultaneous system of equations. Now this concept is also well practiced in degree standard is there. Now that standard is also applicable here through the Laplace transformation. Okay. Now what is the Hankel and Jet transformation, some other applications, and what is the universe of Jet transformations and applications. Now that is the 9th unit. Now 10th unit is fast Fourier transformations. Fast Fourier transforms is interaction, and discrete Fourier transforms and fast Fourier transforms. Discrete Fourier transforms is that the DFT. Fast Fourier transformation is the FFT part is there. And here integral equations and some basic definition of water integral equations, that is the 11th unit. And through the second, the 12th unit is integral equation second part, that is the Fredholm integral equations. And the problems are also practiced here. Okay, next one. Now at the same time here, just you have to see this one. Okay. Now this is the concept of the syllabus. Okay, here that is the total number of units, 18 units here. Now from the here the beginning is the multiple integral part is there. What is the multiple integral? And before that, 13th unit is also here, tensor calculus. Yes, sorry to say here, tensor calculus. What is the tensor calculus and how to already previous from the beginning I have explained here. What is the tensor products? Now this is the purely algebraic concept is there. What is the tensor calculus? Now that the tensors, that is the research oriented in the space region is there, enter the group algebraic level, that is the 22nd stage here. Now through the tensor calculus, how to define the algebra of tensors and the metric, that is the analyzation part is also involved here. That is metric tensor. Metric means that is the distance between the 2 points is there, distance from x to y. Okay. Now according to that metric conditions is also applied here. So what is the metric tensor and the Riemannian space? The Riemannian integrals is కూడా మనం ఏ విధంగా డిఫైన్ చేయొచ్చు అనేది మనం ఇక్కడ చూస్తామండి. So that is the 13th unit. Now here the 14th unit is there, tensor calculus 2. That is the Christoffel symbols and the covariant differentiation and expressions for gradient divergence. Already later I explained here. Through the vector calculus, how to define the now Christoffel part is Christoffel symbol. You have to practice in special functions is also the Christoffel summation formula, and according to that here Christoffel symbol is also practiced here. That is the tensor calculus second part is the Christoffel symbols from the beginning. Now what is the covariant differentiation and here the expressions of gradient. That gradient, divergence, curl, these operators, that is the differential operators through the differential vector geometry. Okay, so that is the differential operators. That is the part. Now that the differential operator is denoted by del or nabla. Now that is the notion is what is the nabla is there, summation I2 by dou x. Now that is the 14th unit is completely based on the basic concept is vector differential operators. First of all, what is the vector differential operator? Now that is denoted by nabla. That is also the simple form as summation I2 by dou x is here. Okay, and these are 3 types differential operators. Gradient, divergence, curl is there, and according to that some other problems are also practiced here. and tensor calculus applications. So the above differential operators must be involved in the concept is already from the beginning is also what is the concept of MAM, methods of applied mathematics concept, already here explained here. Through the vector differentiation, we have to explain the differential vector geometry. What is the tangent of a curve, and according to the tangent vector of a curve is that is the dr by dt is there, some r be the position vector function, and according to that dr by ds, that is called capital T. So that is the unit tangent part is there. Okay, that is the unit tangent part. So what is that is the fundamental vectors are derived from T cross. Okay, some what is the T cross n and what is the B cross n and what about the relation of B cross T. So these three are T and B means unit tangent vector, unit tangent, principal normal, binormal. These are three fundamental unit vectors. These are fundamental vectors, means according to the fundamental vectors, we have to find out the unknown vectors are in the physical phenomena. What is the torsion? Tau. What is the curvature? Curvature is completely based on the, that is the principal normal and the unit tangent is there. Okay. Now, the binormal part is according to the binormal, we have to find out the torsion concept is also well defined here. Now, that is the 15th unit, applications of tensors in differential geometry. And applications of tensors in elasticity. This is the elasticity part is also in the same physical phenomena part. The physical oriented, we have to explain the tensor calculus applications and applications of tensors in fluid mechanics. Already in the first year physics is also we have to see this. Now those concepts are also must be repeated through the kinetic energy, potential energy, and according to that, what is the elasticity concept and some fluid mechanical concepts through the tensors. Last one, 16th one is the green function. That in one dimension, what is the green function in one dimension? And green function for the non-homogeneous sturm Liouville problems. Now in the generalized green function for the non-homogeneous boundary value problem. Next one, green function in higher dimensions are also here. Okay, that is the 16th unit. Now 17th one, perturbation technique 1. Perturbation techniques 1. Now that perturbation techniques 1 part is algebraic equations and the transcendental equations. Those equations, first of all, what is the algebraic equation, and second one is the transcendental equation, and according to that, perturbation techniques are also well defined here. Now, in the same manner, in each the last perturbation techniques 2, second order DE is there. What is the second order linear DE? Already that is also well practiced in using first year. That is the BSc, first BSc is also here. Second order linear differential equation, d square by dx square plus b by dx plus 2y equals to capital R. Now that is the second order differential equation. Now according to the second order differential equation, we have to find out the some other concepts. What is the complementary function and some particular integrals and method of variation of parameters. Changing the dependent variable and the independent variable is also well practiced in first BS level. But here in the same manner, second order linear DE, second order non-linear DE. How to solve this type of problems and through the perturbation techniques. And some other last one is the last but not least here, and boundary layer problems. Now, this is one of the important concepts in the perturbation techniques too. This is one of the important concepts. These 18 units are involved in methods of applied mathematics. Now, here the first one, we have to see this. What is the multiple integral concept? That is the third unit. Okay, just we have to see here. Please stand there. I'm sharing. You can see this one here. What is the multiple integrals? Just you have to listen carefully. Now, multiple integrals means before that multiple integrals already we have well practiced in vector integrals are also there. That is the integration of vectors. These are three types of integrals. Line integral means that is a single integral part comparatively on both sides here. Now in vector integrals and multiple integrals comparatively on both sides here. Now line integral is also in the same manner. That is closed line integral C f dot dr. Here let f be any vector function and r be the position vector and the dr is the position vector is also denoted by xi plus yj plus zk is there. Now what about the dr dxi plus dyj plus dzk? Okay. Now f dot dr means line integral f1 dx plus f2 dy plus f3 dz. Now these integrals are also well practiced. In the line integral, you have to practice find the line integral through the variation points from one point to another one. Suppose 0, 0 to 1, 1 is there. Now the line integral 0 to 1 is there here. Okay. Now integral 0 to 1, f dot dr is also here. Okay. Next one, second one is the line integral is also according to the line integral. You have to find out the multiple integral concept. That is the single integral is there. Now, in the same manner in vector integration, surface integral is also there. The surface integral is denoted by integral S. Surface means it expresses the double integral of the part over the region. Over the region means here. Now that is the biconditional part. Suppose x circle y plane or y circle z plane or z circle x plane is here. And according to that in xy plane or yz plane or zx plane. Now that is surface integral f dot and ds is also comparatively here. That is the double integration of the part. And triple integral means that is the volume integral of the part. Now first of all we must and we have to understand in a basic level that is line surface volume integral, and those integrals are also well practiced in a UG level. Now according to that you have to practice some other problems are also here. Okay. Now according to that here see this introduction. Here the standard integration is capital I equals to integral a to b f of x dx. Now this is the standard integration must be explained through the Riemann condition. Riemann line integral is there. In between integral a to b we can divide it to there are so many partition points are there. So that is a equals to x0 and b equals to xn. Now here x0 to xn and here explain the close that is integral x0 to xn or f of x dx or numerical integration is also there. That is the standard function represented as capital I equals to integral a to b f of x dx. Now that is the function bounded integrable function is defined on closed interval ab here. What is the closed interval AB? Now here closed interval AB means in between A and B in the real line. Now A equals to x0 and some other partition points in between A and B is here. That is A equals to x0 and B equals to x1. Hello? Hello? Here A equals to x0 and B equals to x and A equals to x0, x1, x2, so on. Or subinterval is xr minus 1, xr. Can you hear me, sir? Hello? Hello? Now, integral, that is standard integrable function depends upon the interval points is in between A and B. That is I equals to integral A to B f of x dx. Here f of x is called the integrand and closed interval AB, the range of integration. Now, those points are called in between A and B is called the partitioned points. Now, those partitioned points must be the form of subintervals, and those subintervals is denoted by I1, I2, I3, and so on. IR. IR is half subinterval is also there. Now, in the same manner, standard integrable function, every subinterval must have one of the length of the subinterval. That is the already we have learned, we have practiced. So on Riemann problems are also in the UG level, especially in the analysis part. Okay. Now here that is integral A to B f of x dx. Now that must vary here. Just see here as a clear part is integral A to B f of t dt. Now they are variable changing with respect to the replacing x by t is there. Now in sometimes now standard integrable function, that is the part is integral a to b f of t dt. This is the a be the lower part and b be the upper limits. Here a be the lower part and b be the upper limit. Now that is treated as integral a to b f of t dt. This is the standard integrable function. Okay, in numerical analysis is also according to the concept is in the standard integration quadrature expression is also there, and some other formulas are also according to the quadrature. You have to find out some other expressions, trapezoidal rule, and some other trapezoidal, Simpson 1/3, Simpson 3/8, and Wedel rule is also there. Now there are so many expressions is defined from standard integration in the Riemann concept in between the partition points and according to the length of the subintervals. Now this is the standard integral function is I equals to integral a to b f of x dx. Now already fundamental theorem of calculus is also there. Now pi is the primitive of the function. Now that is pi dash of t equals to f of x dx is there, f dash of x equals to pi of x, and whatever it is. Now integral a to b f of x dx equal to f of b minus f of a. And some other linear concept is also there. That is the first mean value theorem, second mean value theorem, and the fundamental theorem of integral calculus. That is those theorems, mean value theorems based on fundamental theorem of integral calculus. That's enough. Now that is the integral function. Now here the double integral expression, and before that, what is the line integral of the part? Already explained here. And those line integrals must be referred as the line integral means that is the single integral part. Must be referred as the line integral here. Now that type of integral how to solve, that is the simple part is there. And simple integration calculus is also well practiced in from the intermediate level to and upgrade levels. Okay. Next one. Here the double integral concept is there. This is the one of the important concepts here. What is the definite integral of the part? Here integral a to b f of x dx is defined as the limit of the sum. Now this is the definite integral concept. Now here the definite integral is the proper integral of the part. One integral varies to second integral of the function. That is f of x1 into delta x1. What is the meaning of delta x1? The interval difference is here. That is x1 minus x0. Now in numerical analysis is there, and some of the Riemann concept is also there. Okay. Now already have to practice in the interval difference in the previous sessions. Now that is integral a to b f of x dx is the definite integral defined as the limit of the sum. That is f of x1 delta x1 plus f of x2 delta x2 so on f of xn delta xn as intensity definition is there. Here the delta xi is always approaches to j 0. Here I varies from 1 to n representation. Now this is the counterpart in two-dimensional part. Yes, that is double integral part is the two-dimensional part. Now each integral represents one of the dimension is there. Either x-axis, one integral x-axis or another one y-axis, and the yz plane and the yz dimensions and zx dimensions are also referred to here. Now that is called a double integral concept. Now here the clear definition is there. Let f be a continuous function of x and y defined within and a region R bounded by a closed curve script C. Okay. Now f be a continuous function. The continuous function of x and y, a region R, and that function must be represented in the region is R bounded by a closed curve, means closed curve C is there. We shall subdivide it in the region R arbitrary into n subregions. Already I have explained here. Now that is delta A1, delta A2, and delta AN. Now here let zeta and eta I be any points on the subregion of area delta I. The variation of delta A, interval difference of the variation is represented as here in here zeta one of the point and eta, and this is the one of the point with respect to zeta and eta. Now what is the consider of the summation here? Summation f of zeta and eta into delta ai. Here if the limit of this sum as n tends to infinity, delta a is always approaches to 0 exists. Now interval of the difference must be approaches to 0 exists. Then it is defined as the double integral of f over the region. Now simply written as double integral of the concept, that is R double integral f of x by dA. R double integral means double R means that is the region of the part. that region along the xy dimension or yx dimension, yz dimension or zx dimension, whatever it is. Okay. Now here r double integral f of x by dA means r double integral f of x y x and y dA equals to, that is the limit nature is there. Limit summation is also well known part in Riemann integral calculus. Integral as the part of a sum. Okay. Now according to that, r double integral f of x by dA equals to limit summation f of zeta and eta I values of delta ai. This is the double integral of the summation. Okay, that is double integral r f of x by dA equals to, simply that is the notion of this part. Now double integral located as r double integral means r means that is the region. That region must be located either xy dimension or yz dimension or zx dimension is here. Okay. Now that is limit tends to infinitive. That is summation f of zeta and eta I values of delta ai representation. Okay. This is the definition of double integral of the part through the summation nature. Next, some other properties of the double integral. See here, the following properties of double integrals follow from the definition of double integral. Suppose r double integral k f of x y and dx dy is there. That is k into r double integral f of x y dx dy. Here k be any one of the constant, and here f and g are continuous bounded functions defined on a region Kepler on the xy plane. Previously here explained here. Now double integral nature through the xy dimension or yz dimension or zx dimensions here. Okay. Now the region is xy plane of the region through the functions f and g, both are continuous bounded functions. Now given the functions are continuous bounded functions, here especially k be the constant here. Okay. Now constant of the double integral function means constant of double integral. Double integral of constant function equals to constant of double integral function. Okay, and in the same double integrals, another property is there. Now in the area plus or minus here, say in between two functions of the double integral is now plus or minus of the individual of the double integrable function. Now it read as here r equals to, r can be divided into r1 and r2 is there. Now double integral of r f of x y plus or minus double integral of r g of x y dx dy. So double integral of the any two functions in between of the either addition or subtraction. Now here the individual of the either addition or subtraction of the double integrable function. Here R means the union of R1 and R2. There are two types of regions. Off region and off region is there. There are two. One region is R1 and another region is R2. Okay. The union of the two regions is represented as Kepler. And here the third one is r double integral of f of x y dxy equals to r1 double integral f of x y dxy plus or minus r2 double integral of f of x y dxy. Now here's the evaluation of how to find out the evaluation of double integral of this part. Now it is possible, suppose how to find, given the observation clearly here, given the function is there, that function whatever it is, either x square plus y square minus 1, whatever any function is there in terms of x and y. Now the function is given, and how to evaluate the double integral of the part. Now one integral varies from x1 to x2, another integral varies from y1 to y2. Now that is the base values are x1 and y1 is one of the interval, x2, y2 is another interval. Now from one point to first coordinate, from 1 to 1, x1 to varies from x1 to x2 and varies from y1 to y2. Now here the characteristics, just you have to observe this case one. So this is the dimensional part is there, graphical representation. There are two functions, f1 y function. So here x equals to f of y function is there. We are taking the two values x1 and x2 is there, and x1 equals to f1 of y and x2 equals to f2 of y. Here the curve is AB is one of the curve, and here the curve is CAD is also one of the curve is there. Those curves and connectivity in between these two curves, A to C and B to D, represented both connected these two curves. Now this is the Kepler region. This region is called Kepler. In between, now the midpoint is AB, midpoint is on B of the curve is P, and the CD curve in between the point is Q is there. Now here the R is the mean of that is the region. The region in between P and Q is there. Okay. Now we have to observe the double integral of the nature is case one. Suppose here there are two functions x1, x2 functions of y. The y1, y2 are constants here. Now the integrand of the function with respect to x, keeping y fixed within the limits x1 and x2, and the resulting expression is the integrand with respect to y between the limits y1 and y2. Now that is the notion of I equals to integral of, first of all you have to take in the value is x part is there. You have to solve the x part because y is the constant part. Now that is the y varies from y1 to y2. And the second one, now in the bracket region, first of all you have to solve it. Now that is integral of x1 x2 f of xy dx of dy. Okay. Now that is the case one. Now this process is in the geometrical path is also here. Now at the same time, these two terms depends upon the vertical path. Okay, that is y1 and y2 because there are two constants here. Y1 and y2 constants are here. Okay. Now A, B, C, D represents. Now that expression is also defined as clearly here. Now A, B, C, D represents. A, B is one of the curve and C is also represents the curves. Now of the curve of the functions means x1 equal to f1 of y curve is AB and x2 equal to f2 of y curve is CD. Now this is the horizontal strip of width dy. The inner integral indicates that the integration is to be done along one edge of the strip. Okay, just have to see this one. Okay. Yes. Yes. Now, the inner integral indicates the integration is to be done along one edge of the strip from P to Q, while the outer integral corresponds to the sliding of the edge from AC to BD. This is the part. Okay. This is the sliding part. Y1 varies from Y1 to Y2. That is AC to BD. Okay. Now that is from P to Q is also there. Now another case one, here the next one, x1, x2 constants and the y1, y2 are functions. Now how to solve this one? That is I equals to, first of all you have to, x part is also taken outside of the integration. That is integral x equal to x1 to x2. And first of all you have to solve the y function, y integrable function. Now according to that, then totally entire part is also converting into the x part, and is also have to solve the other integration is x part. That is integral x varies from x1 to x2 of dx. Okay, this is the second case of the part. One case is x constant, x value, y value is constant. Now, this particular strip through the along the y-axis, and another one is not from the last one you have to solve in terms of x values. So that x integrand